projects. In this video, we are going to explain about brain hemorrhage detection based on heat maps, autoencoder and CNN architecture. Introduction. The project covers the use of deep learning and machine learning approaches to study of medical data sets with a focus on the identification of brain hemorrhage. Brain hemorrhage is a dangerous condition that, if not treated promptly and appropriately, can result in stroke or death. The research describes a study in which CT scans of patients suffering from cerebral hemorrhage were classified utilizing a convolutional neural network model CNN, autoencoder structure and heat map method to improve classification success. The project also includes a synopsis of similar studies in the topic. Objective. The project's goal is to use deep learning and machine learning techniques to provide a diagnostic approach for brain hemorrhage identification. The specific goal is to increase classification success by classifying computed topography CT pictures of brain hemorrhage utilizing a convolutional neural network CNN model, autoencoder structure and heat map approach. The research also intends to use data augmentation techniques to enhance the number of photos in the dataset and to do classification using support vector machines. The ultimate goal is to increase the accuracy of diagnosis for this dangerous condition by contributing to the classification of cerebral hemorrhage image. Requirement. The requirements of the project are hardware requirements and software requirements. In hardware requirements, we have operating system Windows only, processor i5 and above, RAM 4GB and above, hard disk 20GB and above. In software requirements, we have Python IDEL with 3.7 version. Methodology. To implement this project, we have designed the following modules. The first module is Upload Brain Hemorrhage Dataset. In this module, we collect a dataset containing brain scan images, each labeled with information about whether a brain hemorrhage is present or not. The dataset should be appropriately annotated with binary labels 0 for no hemorrhage and 1 for hemorrhage. It is essential to have a diverse and balanced dataset to ensure the model's effectiveness. Second module is Dataset Pre-processing and Heat Map Features. Before feeding the data into the model, it undergoes pre-processing to ensure it is in a suitable format for training. Common pre-processing steps include resizing all images to a uniform size, normalizing pixel values and converting the images into numerical arrays. Data augmentation techniques such as rotation, flipping and shifting may also be applied to augment the dataset and improve generalization. Heat map features refer to the process of generating visual explanations of the model's prediction. Techniques like GradCAM, gradient weighted class activation mapping, or CAM class activation mapping are used to create heat maps. These heat maps highlight the regions in the brain scan images that were most influential in the model's decision-making process. By visualizing these regions, we gain insight into which parts of the brain scan contribute to the model's prediction of brain hemorrhage. Third module is Run AlexNet Features Extraction Algorithm. AlexNet is a deep convolutional neural network architecture that can be used for feature extraction. In this module, the pre-trained AlexNet model is loaded, often pre-trained on a large dataset like ImageNet, and the fully connected layers are removed, leaving only the convolutional layers. These convolutional layers act as feature extractors and can transform the input brain scan images into a set of high-level feature representation. Fourth module is Train SVM Classifier on AlexNet Features. The feature extracted by the AlexNet model in the previous step are used as inputs to train a support vector machine SVM classifier. SVM is a popular machine learning algorithm for binary classification tasks. It aims to find the optimal hyperplane that best separates the feature representation of brain scans with hemorrhage from those without hemorrhage in the feature space. SVM is chosen here for its ability to handle high-dimensional feature vectors effectively. Fifth module is Predict Brain Hemorrhage from Test Images. In this step, the trained SVM classifier is applied to predict whether a brain hemorrhage is present or not in previously unseen test brain scan images. The test images go through the same pre-processing steps as the training data, and the features are extracted using the pre-trained AlexNet model. Then the SVM classifier predicts the probability of hemorrhage based on these features. Sixth module is AlexNet training graph. The AlexNet training graph represents the progress of the training process of the AlexNet model. It displays the training loss in accuracy over epochs. The training loss shows how far of the model's predictions are from true label during training. The accuracy metric reflects how well the model is performing on the training data. Monitoring the training graph helps in understanding if the model is overfitting or underfitting, and if further training is needed. Execution. For the execution of the project, we need to open the code folder. This is the code folder. This is the dataset folder. In the dataset folder, we have no folder and yes folder. In the no folder, we have the normal images. That is, these are the images which are not affected by brain hemorrhage. And in the yes folder, we have the hemorrhage detected images. And this is the model folder. This folder contains pickle files stored, which contains algorithm information. These pickle files can be loaded into the project code during runtime to utilize train models. And this is the test images folder, in which we have the test images which we have utilized in the project. And this is the main code file. This is run.bat file. Instead of executing a project in the command line interface, we have created Windows bat file to execute the project. Double click on run.bat file. A graphical user interface will pop up. This graphical user interface is created by using Tkinter in Python. By using this graphical user interface, we will interact with the project. Now click on Upload Brain Hemorrhage Dataset to upload the dataset and select Dataset. So here we can see that the dataset is loaded. Now click on Dataset Pre-Processing and Heat Map Features to read each image and then calculate heat map and then normalize pixel values and then split dataset into train and test. So this is the heat map image. We'll close this. Now click on Run AlexNet Feature Extraction Algorithm to train AlexNet and get the output. After training AlexNet, we will get the AlexNet accuracy, precision, recall, F-score, sensitivity and specificity. And this is the confusion matrix of AlexNet. X-axis represents the predicted class and Y-axis represents true classes. And the blue color boxes contains incorrect prediction and the light green and yellow color contains the correct prediction. So here we can see that we are having one incorrect prediction and two incorrect prediction. Now we will close this. Now click on Train SVM Classifier on AlexNet to train SVM. After training SVM, we will get the accuracy, precision, recall, F-score, sensitivity and specificity of SVM on AlexNet feature. And this is the heat map of SVM on AlexNet features. On x-axis we have the predicted values and the y-axis represents the true class. So the light green color and yellow color represents the correct prediction and the blue color represents the incorrect prediction. So here we can see that we are having only one incorrect prediction. Now we will close this. Now click on Predict Brain Hemorrhage from Test Images. And here I am selecting 2 JPG image and open it. So this is the heat map image of this particular image. We will close this. So here we can see that SVM classification is brain hemorrhage detected. So this is the image of the person in which the person is infected, detected by brain hemorrhage. We will close this. Now we will select another image and predict whether it is brain hemorrhage detected or not. So this is the heat map of this particular image. We will close this, and the SVM classification is no brain hemorrhage detected. That is, the person is not infected by the brain hemorrhage. Now we will click on AlexNet training graph. So the x-axis represents the training epoch and the y-axis represents the accuracy and loss, and the green line represents the accuracy and the red line represents the loss. So here we can see that with each increasing epoch, accuracy got increased and loss got decreased. In the above graph we can see training accuracy reached closer to 1 and loss reached closer to 0. We will close this graph, and the final conclusion of the project is the experiment concluded that the proposed strategy utilizing the CNN model, autoencoder structure and heat map method aided in the classification of cerebral hemorrhage images. Because the study's data collection was inadequate, data augmentation approaches were used to ensure the validity of the proposed approach. The results revealed that the autoencoder model and the heat map method increased the proposed model's generalization capabilities. According to the study, picture reconstruction on the data set contributes to classification outcomes. These strategies will be tried on different CNN models in future studies using different data sets.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.